Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's class. In last few classes, we have been discussing the problem of harmonic oscillator and how we can solve this problem through quantum mechanics. To recall, we have written down the Hamiltonian of the harmonic oscillator problem. The Hamiltonian had a kinetic energy term and a potential energy term. The kinetic energy term is given by the operator p square by 2m and the potential energy term is given by the operator half k x square term. So, here p is the momentum operator and x is the position operator. We also discussed that instead of using the linear momentum and the position operator, we can express these two operators in terms of two new operators that we call step up or step down operators, and we can express this Hamiltonian as h bar omega a plus, which is step up operator, a minus, which is step down operator, plus half. So, this is the new form of the Hamiltonian operator that we had been dealing with. If you remember, we called this a plus a minus operator as a new operator called operator n, and we tried to solve the eigenvalue problem corresponding to this operator. While doing so, we defined that let phi n be an eigenfunction of this operator n with an eigenvalue of small n. So, this is what we had defined. Since n is a Hermitian operator, this n is going to be a real eigenvalue. Other thing that we should remember is that looking at this Hamiltonian operator, which is sum of p square and x square operators. If you remember, p is a Hermitian operator, therefore, its eigenvalues are real. It can be positive or negative, but they have to be real. But p square's eigenvalues have to be real and positive. Similarly, x is also a Hermitian operator and its eigenvalues are going to be real, whether positive or negative, but however, x square operator's eigenvalues are going to be real and positive. So, therefore, the eigenvalues of this Hamiltonian operator for harmonic oscillator are going to be real and positive, because this operator is sum of square of two Hermitian operators. So, therefore, the eigenvalues are going to be real and positive. Given that we have defined our Hamiltonian as in terms of this n operator, and then we would see what would we get if we evaluate this particular expression. Since Hamiltonian operator h is defined in terms of operator n as n plus half. So, therefore, I can rewrite this expression and I have this h bar omega, I am bringing it out of this integration. So, when you see this operator n, when it acts on phi n, we have defined that this phi n is an eigenfunction of operator n. So, therefore, the result of this exercise would give us n plus half h bar by omega. So, this is the expectation value of this Hamiltonian operator. Now, this Hamiltonian operator's eigenvalues are going to be real and positive. So, therefore, we can say n plus half is going to be greater than or equal to 0. So, therefore, n is going to be greater than or equal to minus half. So, when we started defining our eigenfunctions of this operator n, we just said that let n be an eigenvalue. We did not know anything about n, but now we see that this value n cannot be smaller than minus 0.5. It has to be greater than or equal to minus 0.5. Mind you, we still do not know what are the values of n or what is the lowest possible value of n, but at least from this exercise we get to know that there is going to be a lower limit for the value of n. If you remember we defined our eigenfunction as phi n with an eigenvalue of n. We also suggested, if you remember the discussion of from the last class, what the step up and step down operators do. So, we said that if I apply my step down operator on phi n, I will generate phi n minus 1 function. If I apply step down operator one more time, I am going to get phi n minus 2. If I start applying step up operator instead of step down operator on phi n, I am going to get phi n plus 1. So, this is the action of step up operator and this is the action of step down operator. So, step down operator brings me down the eigenvalue spectrum, step up operator takes me up the eigenvalue spectrum. Now, since phi n are the eigenfunctions of the Hermitian operator n, so therefore, they are going to form a complete set. So far I did not know what are these, whether there was any upper limit or lower limit to this n, but now thanks to this exercise I now know that there exists a lower limit of n. Now, if there exists a lower limit of n below which the eigenfunction should not exist, that means suppose I want to find out what is the lowest possible eigenfunction. I call that phi minimum, that is the lowest function. Now, if I have this lowest function phi minimum and I apply the step down operator on it. So, I have this phi minimum which is the lowest eigenfunction of operator n, and I apply my step down operator on this function. What would I do? What would I get? See, step down operator's job is to take the eigenfunction and give you back the eigenfunction just below it. But now, since we have defined phi minimum is the lowest eigenfunction, since it is lowest eigenfunction, there exists no other eigenfunction below it. So, therefore, this exercise should give me 0. This is what we discussed, this is what we have learned from this exercise. Now, suppose this, so therefore, if this is the lowest allowed eigenfunction, action of A minus will give me 0. Now, what is the eigenvalue? So, this phi minimum is the lowest eigenfunction of operator n. If this is the lowest eigenfunction, the question that we are asking is that what is the eigenvalue corresponding to it. So, if you remember n we have defined just here A plus A minus operator, the step up step down operator, and then we are applying phi minimum here. Now, when you look my A minus operator, when it acts on phi minimum, what do I get? Since phi minimum is the lowest eigenfunction, step down operator should give me 0, because there exists no other eigenfunction below phi minimum. So, therefore, this A minus operation on phi minimum gives me 0. So, therefore, the outcome is 0, which I can rewrite as 0 multiplied by phi minimum. What advantage do I get by writing in this way? So, if you look at the left hand side and right hand side, you see that left hand side shows operation of operator n on phi minimum, and the right hand side shows that I am getting back my function with a constant 0. So, that means phi minimum is an eigenfunction of operator n with eigenvalue of 0. So, does this satisfy the other limit? The limit that we have found from this exercise is that the n value of n should be greater than minus 0.5. It could have been minus 0.4, it could have been minus 0.3 or any other number, real number above minus 0.5. But this exercise over here tells me that the minimum value of n, the minimum eigenvalue n is going to be 0. So, therefore, phi minimum I can write as phi 0. So, the lowest possible value of n is going to be 0. Now, this is the lowest eigenfunction of this operator n. But remember, we are interested in the operator Hamiltonian operator. Hamiltonian operator is closely related to this n operator. So, now we have seen that the lowest eigenfunction of n operator is phi 0, but now the question is what would I get when I apply this Hamiltonian on this lowest eigenfunction. This we will look up next. So, H is Hamiltonian operator is defined as n plus half into h bar omega, and we saw that phi 0 is the lowest eigenfunction of operator n with this relation. So, if I apply this phi 0, if I apply the Hamiltonian operator on phi 0, what would I get? So, the Hamiltonian operator is given like this and application of phi 0. So, when n acts on phi 0, I get 0, and then if you do this little exercise, you would get. Now, what do I see? I see that phi 0, the lowest eigenfunction of operator n, and since this is the only operator that is defined in Hamiltonian. So, this is also the lowest eigenfunction of this Hamiltonian operator. So, the lowest eigenfunction of this Hamiltonian operator corresponds to an energy value of half h bar omega. So, this is, since phi 0 is the lowest eigenfunction, that means the corresponding eigenvalue is the lowest possible energy of a harmonic oscillator, and this value is also known as 0 point energy. This is known as 0 point energy, that this is the minimum energy value of a harmonic oscillator. Alright. Now, we know the lowest eigenvalue. What about the other eigenvalues? Because we know that this Hamiltonian operator is a Hermitian operator and it is going to have a complete set of eigenfunctions, and we would be interested in knowing the eigenvalues of the other eigenfunctions. To do that, I will remind you of a little exercise that we did in some earlier class. We discussed that if phi n is an eigenfunction of operator n with an eigenvalue of small n, we have already shown that we say that if phi n is an eigenfunction of operator n with an eigenvalue of small n, then a plus phi n, that means step up operator acting on phi n, this is the eigenfunction, step up operator acting on that eigenfunction is also an eigenfunction of this operator n with an eigenvalue n plus 1. So, we would remember this expression and use this relation to calculate other eigenvalues of the Hamiltonian operator. Okay. So, suppose let us say I am starting with n equals 0. So, when I do this, I would actually write down n a plus phi 0 is, since n is 0 over here. So, I am getting 1 into a plus phi 0, but I know this a plus phi 0 is proportional to phi 1. Phi 1 is the next eigenfunction. So, n phi 1 is 1 phi 1. Similarly, if I apply n equals 1 in this expression, I get operator n acting on a plus phi 1 gives me n is 1. So, here I get 2 a plus phi 1, but I also know that this a plus phi 1 is proportional to phi 2. So, therefore, I can write down that n phi 2 is 2 phi 2. Similarly, I can show for all other phi values, and I come to this general understanding where n phi n is the operator n acting on phi n gives me eigenvalue of n, but now I know something more about these eigenvalues. What do I know? The eigenvalues that I am getting are 0. This is where I got when n is 0. When n is 1, I am getting eigenvalue is 1, 2. So, now I see that the eigenvalues of this n operator are nothing but integers 0, 1, 2, 3, 4, so on. So, this is quite a surprising result, because we see here a Hermitian operator which corresponds to a physical observable has eigenvalues that are dependent on the integers, the numbers that we use to count. So, this is the beauty of quantum mechanics that we are seeing. So, now we obtain the eigenvalues of n operator. We will just rephrase this and discuss the eigenvalues of the Hamiltonian operator. So, Hamiltonian operator is given like this, and if I have h acting on phi n, which is essentially h bar omega n plus half acting on phi n. So, operator n acting on phi n gives me small n phi n plus half acting on phi n gives me this. So, now I see that h operator, the Hamiltonian operator, when it acts on these eigenfunctions phi n, I am getting these eigenvalues which are h bar omega into n plus half, where n is 0, 1, 2, so on and so forth. So, if n is 0, that is the lowest eigenvalue, n is 0, what is the energy? That is E 0, the 0 point energy is simply h bar omega divided by 2. When I apply n is 0, so 0 plus half is half h bar omega by 2. So, when n is 1, I get the next energy level, and that is E 1. If you see this, n is 1, so 1 plus half 3 half. So, I am getting 3 half h bar omega. Similarly, when I get n is 2, the energy E 2 is 5 half h bar omega, and so on. So, now what I am getting is that the energy levels of this harmonic eigenvalues of this harmonic oscillator problem, where the energy levels are given by these quantities, and if you already notice, the spacing between two consecutive energy levels of harmonic oscillator are constant. So, they are all h bar omega. Please remember or refresh your memory as to what was the spacing between two consecutive energy levels of particle in a one dimensional box problem. The lowest energy of this harmonic oscillator that we see, as I have already mentioned. So, this is called 0 point energy. So, we have now obtained an understanding about the eigenvalues of the harmonic oscillator problem. Now, next what we will do is that we will discuss the eigenfunctions of harmonic oscillator. So, we have defined our eigenfunctions as phi n, but still we do not know actually what are the functional form of phi n. But what we have already known, one important quantity, one important information is that the lowest eigenfunction is my phi 0. This is the lowest eigenfunction. Now, if this is my lowest eigenfunction, if I apply a minus operator on this lowest eigenfunction, I am going to get a 0. This much I know, but I still do not know what is phi 0, what is the functional form of phi 0. This is what we are going to do. If you remember, we defined our a minus operator, the step down operator, as beta by root 2 x plus I p m omega phi 0. So, this is the definition of a minus operator that we had defined in terms of x and p, the position and momentum operators. So, since beta by root 2, beta is a constant, which is beta square is m omega by h bar. So, therefore, this is a constant for a non-zero constant for a particular problem. So, I can ignore this term or take it to right side, and then I have x plus I by m omega, and p operator is, so I have only one variable. So, I see I minus I, that gives me plus 1. So, I have x plus h bar m omega d by dx phi 0 is 0. This is, here I just use the definition of p operator, momentum operator. So, I am going to solve this equation. And therefore, I take this and now I separate the phi 0 term on one side. So, I bring phi 0 to the this side and x terms on the other side. And what I am going to do is that, you remember this m omega divided by h bar is a constant. So, I am going to integrate both sides, and I have already done a few times this kind of integration. So, this the left hand side will give me ln phi 0, and if you remember, this m omega divided by h bar was beta square, and the integration of x dx would give me x square divided by 2 plus a constant of integration. I am calling it ln a, which is where a is a constant. So, I can rewrite this phi 0 as a, which is coming out of the constant of integration, multiplied by e to the power minus b x square by 2. So, this is my the functional form of the lowest eigenfunction of harmonic oscillator. So, remember how we come to this functional form. In this case, we actually did not derive all the eigenfunctions through one general expression, but what we are doing is that we are using this concept of step up step down operator and found out the lowest eigenfunction, the functional form of the lowest eigenfunction by using the definition of this step down operator, and then we have this functional form. Now, what is this? If you look at this form, this is e to the power minus some constant x square type of form, and this form is called a Gaussian function, e to the power minus some constant multiplied by x square. So, this Gaussian function has a bell shape. This is x is 0 and this goes from minus infinity to plus infinity, and this function has some other interesting property, is that this is an even function that you can already see. For example, we define a function as even function where f of x is equal to f of minus x, and if f of x is negative of f of minus x, then this is an odd function. If this equality holds, then this is an even function. So, this Gaussian function is an even function because this is symmetric with respect to this 0 axis. So, what we obtain now is the functional form of this wave eigenfunction, but what we do not know is this constant a. How do we get this? Since we have only one constant unknown here a, and if you remember, a necessary condition to have a well behaved function is that it should be normalizable. So, this function we have to normalize, and once we normalize this function, we will be able to obtain what is the value of a, and this is what we would try to do next. So, we would normalize the lowest eigenfunction. So, if phi 0 is a e to the power minus beta square x square divided by 2. To normalize this function, so I have to have phi 0 star phi 0 dx where it goes from minus infinite to plus infinite should be equal to 1. Now, phi 0 is the function you have, phi 0 star is its complex conjugate. So, since this is, but this is a real function, there is no imaginary root. So, phi 0 star is essentially phi 0. So, I write like this, a square, this is the constant, I am bringing it out, e to the power minus beta square x square dx. So, this is how do I get beta square x square, because there is divided by 2 in each term. So, phi 0 and phi 0 star will have this half e to the power minus beta x square divided by 2. So, when I multiply them I get e to the power minus beta square x square dx. Now, I have to integrate this function, but before that I rewrite. So, this I am going to integrate this function. I already have discussed that this is a Gaussian function which is an even function and is symmetric with respect to the 0 axis. So, therefore, what I would do is that instead of using this minus infinity to plus infinity limit, I will change the limit to 0 to infinity, because if a function is symmetric, then its integration or the area under that curve is going to be same when I integrate from 0 to plus infinity or 0 to minus infinity. So, therefore, instead of integrating it from minus infinity to plus infinity, I am going to use this rewrite this in this way, where now the reason behind bringing my form to bringing the integral to this form is that now I am going to use this particular expression to find out what is the value of a. So, I have a square 2 and the result of this integration is going to be, if I here this is the form of the function x to the power 2 n e to the power minus a x square. So, here n is 0 because we have no term with respect to x. So, this is n is 0 e to the power minus a x square, where a is simply beta square. So, when I apply this I would be getting the result. So, this term will become 1 over 2 and this term will be pi divided by beta square. This quantity is going to be 1. So, I solve this, because why is this going to be 1? Because I am trying to normalize this function. So, I have therefore, I have a square into pi divided by beta square under square root is 1. So, therefore, a So, this is my normalization constant, and the final eigen function, the normalized form of the eigen function, if I have to write down, this would be So, now finally, we came to a point where we have some idea about what is the functional form of this lowest eigen function of this of the harmonic oscillator problem. So, in today's class, just to remind you, we discussed the eigenvalues of the harmonic oscillator problem. We also discussed the functional form of the lowest eigen function of this harmonic oscillator problem, and also we normalized this function lowest eigen function. In next class, we will continue our discussion on the other eigen functions of harmonic oscillator problem. Thank you for your attention.